Hello, in this video let's discuss fourth question of today's contest. You are given an integer nums. A subarray of nums is called stable if it contains no inversions. There is no pair of indices I less than j such that v of I is more than v of j. You are also given a 2D integer array queries of length q where q of I is equal to li, ri represents a query. For every query li and ri, compute the number of stable subarrays that lie entirely within that segment v of li and ri. Return an integer array answer of length q where answer of I is the answer to the ith query. N is up to 1 if I, values are up to 1 if I, and queries length are also up to 1 if I. For example, if I have 312 and the query is 01, so we have to find the number of subarrays which completely lie in 01 and without no inversions. And finally we have written the vector of answer. So now what it means there is no inversion? So it means that there should no pair such that if I more than j, v of I is less than v of j. So this something like this should not be existing. So what it means? It means that for every if I is more than j, v of I is also more than v of j, more than or equal to v of j, right? Because it should not be less than, so it should be greater than equal to. So if I is more than j, for every pair I and j such that I is more than j, v of I should be greater than equal to v of j. What it means? It means that, for example, we are at index I. At any index more than this, it should be greater than or equal to this number. So what means? It means it is sorted subarray. So simply now what we have to find? So now given a subarray I to j, we have to find the number of sorted arrays in the range I to j such that end point also lies in I to j and start point also lies in I to j, right? So that is what entirely lying in I to j means. So it should not be like starting at somewhere I before and ending at middle of I and j. Not like that. It should be start within an index which is in I to j, and it must start an index between I to j, and that is what entirely subarray means. And it is given that single element is also considered as a stable subarray. So we have to find the answers for such kind. So now let's discuss an easy and similar version of this. So if we try to get this, then we can try to increase our answer. So now, so what the question is saying, we have to find the subarrays entirely lying within that subarray, right? So what if there is no condition like that? So what if um, we have to find the number of subarrays ending at any of the I to R, I to J in given query. So now for example the query is I to J. So now the easy question says that we have to find the number of subarrays in I to J such that it is ending at some index I to J. It can start anywhere, but it must end at I to J. At an index between I and J. Then how to find it? That is easy, right? Because we can find the number of subarrays ending at any index which are sorted. How? We can simply linearly traverse and then we can check based on the present value and before value. So for now we are at 1. So this is sorted. So the number of arrays, subarrays ending at this which are sorted is 1. And now came to here. So even it is 1. So this is still increasing, kind of increasing, right? So 1 is also counted, double 1 is also counted. So what are the number of subarrays ending at the second index 1 which are sorted? So it is 2. So it is 2. And now come to 2 again. So coming to 2, even now this is increasing. So 2 will come, 1 1 will come, and 1 1 2 will also come. 1 2 1 1 2. So it is 3. And now let's come to next one. So if we came to 1, now it broke because we decreased it from the before value. So now new subarrays are 1. And now coming to 1 again 2, and coming to 3, and coming to 4, and coming to 2 again 1, again 2, again 3, again 4. So in this way we can find the number of subarrays ending at any index very easily and often. So now we have to find in queries range. So given I to j, we have to find sum of all those. So given some queries of I and j, how can we efficiently find the sum of elements within those values? Simply we can use prefix sum. So let's say we got 1 2 3 1 1 1, right? So if this is the case, then we have to find the range in this 1 to 4. How can we do? So 1 to 4, what can we do? We can store the sum till every index, prefix sum. So here 1 it is 1, and till here it is 3, till here it is 6 7 8 9. So what is the use of storing something like this? So if we have sum from 0 to every index, if we want the sum between any two indices, we can get that in O of 1, right? Because for example we want sum from I to j, so we have already sum from 0 to j, so 0 to j minus sum from 0 to I minus 1. So if we do something like that, then only I to j will remain, right? That is what we exactly want. So in this case we can simply use O of n, and we can use prefix sum to get answer in O of n. But now this is not the case. Now the question is saying that the subarray should entirely lie within that range, but here there is no guarantee, right? So now how can we check? So if we clearly kind of observe, so if we try to observe, let's take a simple example. So if this is the case, then start from 1. So what are the subarrays starting from 1 which are increasing? 1, 1 to 1 to 4, from 2, 2 to 4, from 4 only 4, from this 2, 2 to 3. So now let's consider only subarrays like this, because if we consider this or this, both will be considered, but only one should be considered so that there will be no duplicacy. So now for this 2, 2 to 3, for this 3 only 3, for 1 only 1, 1 5, 1 7, for 5 only 5, and 5 7, for 7 only 7, and for 6 only 6. So in this way if we try to observe, every value, for example let's take this one. So if we take this one, it is stopping somewhere, right? So it is stopping at this 4. For example if we have 1 1 1 2 1 2 1 to 4, this is not possible. 1 2 4 3 is not possible. So if we clearly observe, for any index, from any index, it must stop at any index j, right? Because if we are increasing and we got a less value, so we cannot continue this array further, right? So for every index I, there is some kind of in right index j where it must stop, right? Whether that may be because of decreasing value or maybe because of completion of array. But for every index I, we will have some kind of index, right index, such that only till that index it can form subarrays which are sorted. So hope you are aligned with this. Now can we try to think like this? So now we have all these values, right? So we have all these values, and now let's say from this index this is the highest value. So if this is the highest index where we are able to find the sorted subarrays from this, it means that this subarray is wholly sorted. It is completely sorted, but not this element. So from here there may be some range of indices where that is sorted, and this may be single, this may be single, and now this may be complex again. So now why we are doing this? Because when we are at I, there is some index j such that it will stop there. So if we stop there, like this is the block, this is the range of, this is the entirely sorted subarray. So hope you got this. Let's check another easy example. Let's say we have 2 1 3 4 2 5, right? So now coming to 2. So starting from 2, what is the highest index j such that it is sorted? It is only 2, because the next index is itself less than 2. And now coming to 1. So coming to 1, what is the largest index j such that starting from 1 it is sorted? It is 1 3 4. So this is a kind of other block, right? Because these two are independent, because there cannot be any subarray starting from 2 ending at 3 which is sorted, because we grouped by regarding that, right? Because why these both are in different blocks? Because before 2 and 3, between 2 and 3 there is some index I such that it cannot form increasing subarray starting from 2 ending at that value. Only then they will be in separate blocks, right? Because we have 1 and 4. So why 1 and 4 are in the same block? Because every value between 1 and 4 is obviously between 1 and 4 itself. There is no value which is more than that. That's why these both are in same block, right? But here 2 and 4, these both are not in same. Why? Because there is an index I, index and value 1, which is less than 2. That's why this broke here, and that's why there is a new block starting from here. And now coming to 2, what is the new subarray? This is 2 and 5. So now we are able to segregate into blocks. So why we are doing this? Why we want this exactly? Why we want this? Because we are trying to break down the problem. Why? Because for example we have this, let's say we have this 2 and this 4. So there is no interconnection between these two, right? 2 and 4, because they both are in different blocks. So we have to do some extra computation for that, right? For example, So hope you got this first intuition right. So why we are trying to break into blocks? So why we are breaking? Because we found that starting from any index, at any index, right index j, that must stop, right? And why it is stopping? Because till then the subarray is sorted, but after that the array is not getting sorted. Maybe there is no index, or maybe there is an index I which is less than the index which we left it. So that is why we are breaking into blocks, because every two blocks are not dependent. Why? Because they will be in different blocks only when there is some middle value which is less than that. And if they both are in same block, it means that the whole subarray between that is sorted. So hope you got this. So now we got the first intuition. And now coming to queries. So now how can I handle? So is there any simpler way now, or we have to do something more? Let's check that, right? So now we broke that into blocks. So we broke the given subarray into blocks. So now let's say we got first query. We are thinking only about first query, and the first query says 0, 1, 2, 3, 4. So from 4 to 6, we have to return the total number of sorted arrays that entirely lie within the range 4 to 6. So now what is the answer? So if we clearly observe, I already made these blocks regarding the before conditions, and now it means 4 and 6 both are in the same block, right? So what it means? It means that entirely this 4 to 6 is sorted. Else why these both would have been in the same block? 4 and 6 must be in different block if there is no element between 4 and 6 which is making the array non-sorted, right? So it means that entirely 4 to 6 is sorted. So now it is very easy to find the answer. Why? Because 4 to 5 entirely sorted. So 4 is sorted, 4 5 is sorted, 4 5 6 is sorted, 5 is sorted, 5 to 6 is sorted, 6 is sorted. So now what is there? So it means that every subarray in this is sorted. And how can you find the number of subarrays? It is simply size into size plus 1 by 2, right? Because simply we have 3, and we have to find all the numbers, all the subarrays within this. So simply size into size plus 1 by 2. So now if the index is 4, index is 6, these both are in same block, and so we are very confident that 4 to 6 is completely a sorted array, completely sorted subarray. So if this is a sorted subarray, every minimal subarray in this is also sorted, right? If 4 to 6 is sorted, we discussed 4 is sorted, 4 to 5 is sorted, and so on. And what is the count? It is simply size into size plus 1 by 2. So now we got the answer for this query no of 1 very easily, right? Because only that these both are in the same subarray. These both are in same block, These both are in the same block. That's why we are able to make sure that no need to find any answer. We can simply find the size into size plus 1 by 2. So this is easy. But now, what if they both are in the different blocks? So then what? So then, let's say this is the first index and this is the second index. So now we have to find the answer. So here these both are in the different blocks. So simply we cannot do size into size plus 1 by 2, because let's say we have this array starting from this ending at this. So obviously this is not sorted because these both are in different blocks. The starting value and ending value are in different blocks. So this is not sorted. So simply size into size plus 1 by 2 will not help us right now. Now what can we think? So if we are able to think more, right? If we are able to think more, then what? So this is L, and this is the block that is ending where L is present, and there are some middle blocks which are independent of L and R. These are just in the middle. And now this is R. So this is R. This is the block. This is the first index J, and this is the last index I, right? Which is ending of this, which is starting of R, ending of L. So now can't we try to find the answer independently based on the block we are at, right? Because let's say we are thinking about this block. The query is L to R, but we are thinking about this block. So for example, let's take this subarray starting from this and ending at this within the same block. So if that is the case, then this will be included in our final answer, right? Because this is entirely lying in the subarray from L to R, right? So this also will be a part of our subarray, or for a final answer. So what it means? It means that we can simply add size into size plus 1 by 2 of this, and size into size plus 1 by 2 of this also, because every subarray in both of these blocks independently are contributing to our answer, right? Because, so hope you got this. This is very easy, right? because these both are completely sorted, so we can assume that this is the new query, and we can find size into size plus 1 by 2 for this, and similarly for this, and so on within the all blocks. So now this is sorted, so internal part is done, but now other part is left. What is the part? This block and this block. So we cannot get answer from this block and ending at this block, because they are in different blocks. It means we cannot find any answer. So now we have to think only about this block, and we have to think only about this block. And now let's come for the first block. So we are at the first block, we are at L and ending at I. So what it means? It means that every subarray from L to I is sorted, right? Because only then they are in the same block. So now also it became simple if we clearly observe, because L, L to L plus 1, L to L plus 2, and so on till L to L plus I. All these are sorted because these both are in the same block. So even now we can do size into size plus 1 by 2. But now what is the size? Size is simply the number of elements between L and I, right? So only that is the size now, and we can find the answer very easily. And similarly for this also. So this is J, this is R. So R to R minus 1 is a good subarray, R to R minus 2, R to R minus 3, and R to J. All these are sorted. So even now we can get size into size plus 1 by 2, right? So now we are able to get the answer finally in of n. Why of n? Because first, so let's check how to implement that after. But now you got the idea, right? Why we are able to make into separate blocks, and now how to find the answer if both are in different blocks, and how to find if they are in same block. And now let's check the implementation, which is slightly tricky. So what we have to store? So firstly we want one thing. Firstly, if we have I and J, we have to know they are in which blocks, right? They are in which block. So firstly we have to have some kind of map indicating the index and the block ID. So this block ID is 1, this block ID is 2, this block ID is 3. So for example, if we got two values in both block ID as 1, we can simply return size into size plus 1 by 2, right? And now let's check the code. N is equal to v of size, and this is the block ID map, and then we also want the range of blocks, right? Because we have to find these I and j, right? Because we have to find I and j, the largest value which is ending in a block. So what we want, for every block we want the range, starting range and ending value, starting value and ending value within that block. So first block 0 to 3 is in the first block, second block indices 4 to 9 are there. So if I have something like this, then it is easy to find the first value and last value, which are I and j, we discussed exactly, right? So vector of pair, it will store start value and end value for every block. And now start traversing from 1 to n. If this is increasing, if this broke the sorted condition, so till now it is increasing, and now it falls, it means that we are able to get a new block, right? So we are able to get a new block, and when we are getting new block, we have to store old block in the pair, right? So x dot pushback start comma I minus 1. So start is the starting index of the previous block, and it is ending at I minus 1, so simply I minus 1, and push this into x, and then update start, because we made a new block here, so start is equal to I, and then increment the ID, because till now block ID 0 ran, and now block ID is equal to 1 should run. And also after this, update MP of I is equal to ID. So after every index we can update the block ID. So in this way we got all the conditions here itself. And now after completion of the whole array, we have to add this also, right? Because this is the last block, start on n minus 1. And now this is the number of blocks. So now the next thing is, let's say we have 4 blocks. And this is I, this is the query first, and this is query end. So we will find the answer for this independently, we will find the answer for this independently. But what about these 3? We have to traverse through every block in between, and then we have to do size into size plus 1 by 2. Is that really necessary? No, if we clearly observe, no. Why? Because now we can use prefix sum here, because the answer for this block is already computed, which is size into size plus 1 by 2. This is independent of any query, right? So even for this, so simply we can add a prefix vector where it stores the answer for this, it stores answer for this, it stores answer for this, and then we can find the prefix sum, and then whenever we are at different blocks. For example, I is equal to 0 block, j is in 10th block. It means that size into size plus 1 by 2 should be added for every block from 1 to 9. So indirectly what it means that we have to find the prefix sum, that is the number of sum into sum plus 1 by 2 in 1 to 9, and we can get that from prefix sum, right? So now we are storing prefix sums. So simply store size into size plus 1 by 2. So this is the size difference and into plus 1 by 2, and now find the, like, ultimately we have to find the answer. So simply traverse the queries, first value, second value, and find the block IDs of those both. So map of that, block ID of that, block ID of left, block ID of right, and if these both are equal, it means both are in the same block. So simply find the size of both, size of the whole, and continue. Else find the left value in the first block and right value for the second value in the second block, and then find the answer in the leftest block, not leftest, sorry, leftmost block, where this is this is lying, and similarly rightmost block where R is lying. And now find the left count and increment the answer. Right block, right count, increment the right answer, and then we have to increment the answer for the middle blocks. And when can you do that? We can do only when there is some middle, right? For example, let's say we got this 2, and if this is I, if this is j, is there a meaning of adding middle? No, because there is no any middle count, right? So we can add middle only if the right block of right is one more than block of left, only then it means one is middle. So if that is more than, so simply add prefix sum of middle blocks. And now answer push back. If you have any doubts, comment below. See you in the next video.